Hello everyone and welcome to this talk titled CameraReady, Assessing the Influence of Display Types and Visualizations on Posture Guidance. My name is Hesham and I'll be presenting today on behalf of my co-authors Philipp, Sebastian, Martin Schmitz, Martin Weigel, Max and Florian. We developed a posture guidance application that was based on some example application scenarios. First of all, we wanted to support remote motion guidance. That means a two-way communication channel between a remotely located coach and remotely located students. One of the disadvantages of the traditional approach is the necessity of physical presence of both the coach and the students. This is also clearly evident during the recent pandemic times, where physical presence has become increasingly difficult. We also wanted to support mobile training. That means without the use of a coach, the system can automatically classify errors that the user makes and help the user improve his performance. And lastly, we wanted to prevent bad postures that could lead to short and long-term injuries. With our developed application, we evaluated the use of different visualizations for posture guidance. First of all, we used a skeleton visualization, a silhouette visualization, and a 3D body model visualization. These were the visualizations most commonly found in the literature. We also conducted our evaluation using different display types. We used a smartphone, a tablet, a desktop monitor, a TV, and a large display. We based our design on 5 design requirements. Most physical activities such as sports, martial arts, and dance require full body movements. Hence, our system should be able to support the user with full body guidance. Most users also own a variety of devices, for example, smartphones, notepads, tablets, and so on. Our system should be cross-platform to support users on most of these devices. It should also be self-contained. That means it shouldn't require a complex setup, for example, using retroreflective markers and an optical tracking system. It should be mobile. It should support users at a park or practicing at a fitness studio. And of course, it should be person independent in that it doesn't require or it isn't tailored to a specific user. Our contributions are twofold. We introduce a mobile cross-platform system for posture guidance, which we use to conduct a controlled experiment to evaluate the influence of display types and visualizations on user performance. First, I'll talk about our system implementation. We implemented the system using client and server applications. A client application was running on either Android or Windows 10, and the server application was running on Windows 10. We used Unity for compatibility between client and server applications and used a neural network for motion capture. For running the neural network, we used the Unity neural networking package Barracuda, and we used UTexture send receive for handling the camera feed. Lastly, we used Unity mirror networking for synchronization of variables, game object positions, and network messages. Our code is open source and it's available. The link is available in our slides and in our paper. While using the neural network, we conducted an evaluation at the beginning. For that, we used the postures that were performed during the experiment. These postures were performed while wearing retroreflective markers and being tracked by an OptiTrack. A total of 60 postures was collected, 20 per smartphone, 20 with a tablet, and 20 with a webcam. We compared the estimation of the neural network to the ground truth collected from OptiTrack. The plots below show the 3D angle error per device, posture, and device and posture combined. Overall, the neural network had an average error of 5.57 degrees over all joints, postures, and devices, making it comparable to a Microsoft Kinect. We then conducted a controlled experiment to evaluate the influence of display types and visualizations on user performance. For that, we recruited 20 participants, 13 male, 5 female, 1 diverse, and 1 did not specify, all aged between 21 and 43 years old. We had a within-subject study design with 2 factors, display type and visualization. For display type, we had 5 displays, a smartphone, a tablet, a desktop monitor, a TV, and a large display. And we used 3 visualizations: a skeleton, a silhouette, and a 3D body model. We recorded the joint angle error in degrees while the participants were performing the postures. We recorded also the task completion time and the answers to our system usability scale questionnaire. In the end, we also asked participants which visualizations and displays they found most appealing and collected their comments on additional features. With regards to joint angle error, we could not find any significant differences between visualizations. However, we could find a significant increase in error while using a smartphone in comparison to using a desktop monitor, a TV, and a large display. With regards to our system usability scale scores, we found significantly higher SUS scores using 3D body models in comparison to a skeleton visualization. We also found significantly lower usability scores for the smartphone condition in comparison to a tablet, a TV, and a large display. In the end, we collected feedback from our users. 40% of our participants preferred a 3D body model because they found it easy to recognize, most visible, and clear in comparison to other visualizations. 30% of our participants preferred skeletons because they covered the least of their body and allowed them to estimate how they were positioned, and because they had a good mixture between transparency and overlay. And the remaining 30% of our participants preferred silhouettes because it was the easiest way to see what to do. Large displays were by far the favorite display type. 90% of our participants mentioned that they were their favorite display because they made the recognition of display poses effortless and were similar to an expert showing you an exercise. The remaining 10% of our participants preferred the use of TV as it was very pleasant to use. Of course, our work has limitations. We conducted a controlled lab experiment to evaluate the influence of our independent variables. While this provides valuable insights for the future of posture guidance systems, further work is necessary to evaluate how our results transfer to in the wild scenarios. In our experiment, we showed the users static postures that communicated the target positions that the users should take. Further work is required to evaluate how transitions between postures can make it easier for the user, as well as how adding live feedback to communicate the errors helps users with posture guidance applications. Lastly, we used a neural network for motion capture. While this approach is not as accurate as marker-based systems, we are confident that future advancements in the area of computer vision will solve this problem soon. To summarize, we presented CameraReady, a mobile system with a simple setup that works cross-platform for posture guidance. We have assessed the feasibility of our system in a controlled lab experiment using different visualizations found in the literature and the various displays found on the consumer market. Our results show that large displays are both favored by participants as well as show higher usability scores and lower errors in comparison to smaller displays such as smartphones. We also found that 3D body model visualization is more usable than a skeleton visualization that's more commonly found in the literature. Thank you very much for your attention and feel free to ask any questions.